Hi, can you hear me and can you see the screen? I believe I should be audible by now. It's unmuted everywhere. Can you hear me? Can you hear me?
Yes, sir.
Am I audible now? Yeah. So today is the last class of the course from my side. Can you please just confirm once more that I'm audible? I think I messed up something here. Could you please confirm once more that I'm Yes, I believe I'm audible. Okay, so we'll start. So last day towards the end of the class, we were discussing uh, about over excitation and under excitation of synchronous motor. Um, so we got only 2 classes on synchronous motor. Last one and this one. Mostly the problems are solvable using the equivalent circuit, per phase equivalent circuit, and basic power theorems, and that's all. So these three conditions we saw last day um, in motoring mode. So what we have done is we have drawn the circuit, and then we have drawn the phasor diagram for different cases. What are the different cases? First, we took that the current is lagging, that is the motor is operating at lagging power factor. Then we took the current at UPF, and then we took the current leading. These three cases we discussed, and we saw that as the power factor moves, or we should say the other way around, as the excitation moves from underexcited to overexcited, the power factor moves from lagging to leading, whereas for the rated excitation we have unity power factor. So this is a very interesting characteristic of synchronous motor, that you can operate the machine at the power factor you wish, obviously, as long as you are under the rated conditions from all sides, because the excitation is nothing but a DC winding, and it also has a maximum current capability, so you cannot keep on over exciting. And we also discussed about a very interesting topic, that is synchronous condenser, that is nothing but an overexcited synchronous generator, which, as the name suggests, acts like a condenser, that is acts like a capacitor, and it supplies reactive power locally. So if you are not a domestic customer, if you are a commercial customer, that is if you have a factory or something where there is a lot of lagging power requirement, the utility services would bill you for reactive power also, along with the active power as usual. Now, reactive power is something that you can generate at your end by putting this synchronous condenser. We have explained those things in details using phasor diagrams, right? Now, in motor we saw this. Now the thing is, while drawing the generator phasor diagram, I messed up actually. When you multiply something with j, it is rotated anti-clockwise, but since the current was on the other side, and that way I somehow messed up with the direction. So today we will do it once again. Sorry, we will start from here. Generator, we again draw the equivalent circuit. Now notice one thing. Oh, one thing I told wrong in the last class. In this diagram, I told this is delivering lead, delivering lag. This is correct, but this is not lag. This is lead, and this is lag. Okay. All right. So generating. Now notice one thing, that it doesn't matter in what direction you draw the current. This I keep telling every day, that if this is V, this is E, and in generating mode the active power is supposed to flow from the right hand side to left hand side. Active power, let me write active power. Active power is um, written as P though. Active power, that is the definition of generating mode. The active power is flowing out. Whereas for a synchronous machine, the reactive power can flow both ways depending on the excitation that we have already seen in case of motoring mode. However, mm, we can take in any direction. So let us let us take in the direction of v itself, or the other way also we can do. Only thing is you have to make sure that the equation that you are writing is consistent with the circuit that you are drawing. Okay, so let us do one thing. Let us keep the direction of the current same. Let us keep I as usual, right? So the equation does not change. So v becomes obviously a vector ir plus j omega x plus e. So when we are drawing the phasor diagram, this equation will follow. Okay, now we'll start drawing the phasor diagram. So now let us again take v as the reference, phasor. Now as I said that in this case, you see, when I am drawing the voltage and the current like this, if the current is on the right hand side, that means the power is being delivered by v. But it's the other way around, it's a generator now. So the current will be somewhere towards my left hand side. Let us now take first a lagging case. So the current is somewhere here, right? How do I know the current is here? First of all, we took lag, and since it is v is absorbing power, so current should be on the left hand side, left half plane. Because I have drawn the current like that in the circuit. If I draw the other way around, it will change the direction. Okay, doesn't matter. So this is I is lagging. Right now, if this is I, now what we will do is we will basically v minus IR. This operation we will perform. This operation will perform. This will give us E. So if I is in this direction, then definitely, let us say, sorry, IR is in this direction. Let us say this much is the IR. And here where I made the mistake last day, JI omega, oh sorry, why am I writing omega x? It's omega L. J omega x or R plus jx. So I, now jx should be in this direction, anti-clockwise, rotating anti-clockwise. Now minus of jx should be the other way around. So this is minus IR, not IR. Minus IR, and minus j ix. Now when you add them, what you get is E. This is the one, the vector at lagging power factor generating mode. Okay, now let us do the next one, leading power factor. Or no, let us not jump, let us do for UPF, unity power factor. Okay, now unity power factor and V is in this direction. V is in this direction. So I should be exactly the other way. This is I. Now, if this is I, then this is minus IR, and anti-clockwise is this direction, positive. So this is J I X minus. And if I add all these three vectors, what I am getting is E. Okay. And the last one, we are doing for leading power factor. Similarly, we take V in this direction, leading power factor. So the current is somewhere here. Current is somewhere here. So if this is V, then IR is in minus IR is in this direction, and minus J IX is in this direction. So the E that you get is this. Now look at these three diagrams. Clearly, if you see, if you move from diagram 1 to diagram 2 to diagram 3, definitely E is reducing from top to bottom. If you consider E magnitude is reducing, that means the excitation is being reduced. So at rated excitation, you have UPF in generator as usual, like the motor, and under excitation you have lead. Over excitation you have lag. You have lagging current. Understood? Delivered. Okay. So we can quickly write it down for so you have motor and generator. You have under excitation rated excitation and over excitation. So motor over excitation is nothing but the synchronous condenser. So lead. Once you remember this, then it's easy to remember the others. Yeah. So this is the way of operation at different excitation conditions. You have different operating conditions of the machine. Okay. Now, actually, the generator. Let us look at the generator one second. Let us. Mm, what does it depend on? Okay, so this was the generator when it is connected to the infinite bus. That's why V does not change. Infinite bus connected generator. Okay. Displays being lost intermittently. I'm not sure whose issue is that. Might be my issue also. I will close some softwares. Okay. So last day we discussed different types of synchronous machines. One of them was cylindrical rotor synchronous machine, and the other one is the salient pole synchronous machine. All the problems that we had last day was based on cylindrical rotor, and today we have one problem on the salient pole. Now salient pole, as the name suggests, now suppose if I draw only a two pole machine. Okay, now this is say the stator. Like this. Just a sec. Whatever. Now this is a stator, and the rotor is somewhat like this. Okay, two pole structure, simplest one. Now if you see the air gap lengths here along this axis, the air gap length is minimum, whereas here along this axis the air gap length is maximum. Right? Here is the fall. So now if that is the case, suppose um, the windings that are placed, suppose you put one inductor here and you put one inductor here. Say I call this inductor 1 and I call inductor 2. Now at the inductor 1 it will see a higher permeance. Higher permeance because the air gap is very low. Whereas inductor 2 it will see lower permeance. Now this axis that is along the highest permeable axis, highest permeance axis, permeability, permeance, reluctance, PS, permeance. This is called the D axis or the field axis, direct axis. And the one that is perpendicular to it is a Q axis. Okay, so the field excitation goes through the D axis, and we have seen that LD is higher than LQ. True. This LD by LQ is also called saliency ratio, which is greater than 1 for salient pole synchronous machine and equal to 1 for cylindrical rotor induction machine. Okay. Now the problem is with salient pole induction machine. Oh, so last day we had a discussion on this, that in salient pole induction machine we have both kind of torque. We have reactance torque, that is true for cylindrical rotor also, and the another torque component that we get is a reluctance torque component, right? Reluctance torque is simply the ability of a magnet to pull a pair of salient poles, right? It is simply like this. If you make, say, something like this, I will draw a developed view. Say something like this, if you make out of iron, and if you put magnets here like this, so, and if you then move one of them, once they say the set of magnet or this iron piece, this iron, the other will move. That is reluctance, basically. Reluctance torque, reluctance thrust, whatever you can call it. So this is what we get in salient pole machine. With salient machine, we get both reluctance and the reactance torque. Okay. All right. And LD is greater than LQ. Now we will just, although this is not in this syllabus, just for in case you are interested, and these things are kind of trendy also nowadays. That is permanent magnet synchronous machine or BLDC. Actually, they all are synchronous machines. You can call them permanent magnet synchronous machine or BLDC or synchronous reluctance machine or switch reluctance machines. They all are called, all are actually synchronous machines. They are either true synchronous or self synchronous. Okay, auto synchronous or true synchronous. Okay, I will discuss this also. Just this is something that is interesting. So in PMSM or BLDC, as we discussed that day, they don't have the winding on the rotor, they have permanent magnets. Now suppose this is the rotor, right? Is the rotor, sorry, this is the rotor core. Just a sec. The rotor core, let us say. Now the magnet is somewhere. Where to put the magnet? You can put the magnet, say maybe on the surface of the rotor, like this. Four pole structure. Four pole structure, and the magnetization direction is like this. Okay, on the surface, or It may be, or it may be inside the rotor. There are several several topologies also. Okay, like this. So this one here also the direction is like this: outside, inside, outside, inside, like this. Now this is surface permanent magnet, and this is internal permanent magnet. Now this is one thing that you may know already, or if not, then just take my words that permeability yes, permeability mu of permanent magnet is almost equal to 1. Okay, that is same as that of air or vacuum, let us say a vacuum. Now if this is the rotor of an SPM, if this is the rotor of an SPM, above the rotor is, or outside the rotor, that stator is present like this. On the other hand, here also above the rotor the stator is present. Now this may cause confusion. The rotor, the stator is present, whatever. So this is stator, not this. This outer blue color is a stator. Okay, and this is the rotor. Now you see one thing, this one, the SPM, that apparently looks like salient pole. Apparently that looks like salient pole because it has magnets protruding out of the rotor. It apparently looks like salient pole, but as I said that the permeability of permanent magnets is almost same as that of vacuum or air. That means in this case, see, this is the d-axis, and d-axis, and this is the q-axis. Does it surprise you that d-axis and q-axis are not in quadrature, not at 90 degree, not 90 degree apart? They are 90 degree apart. D-axis and q-axis in this diagram also, they are 90 degree apart. They are 90 degree electrical apart. It's a 4-pole machine. So 90 degree electrical is 180, so is 45 degree mechanical. Okay, they are 90 degree electrical apart. So d-axis and q-axis inductances are same, LD equals LQ, although it looks like salient pole. But this IPM is even more interesting. IPM, if you see, this is the d-axis because the magnet flux flows through this, and this is the q-axis. IPM apparently looks like a cylindrical rotor machine, right? The rotor is smooth, cylindrical rotor machine. But if you look at the d-axis, there is a gap in between, an air gap in between. You can call it, it's a magnet, but we know that magnet, as long as we consider the permeability it is as good as air. So along d-axis there is a more gap, along q-axis there is only the air gap. So LD is less than LQ. For this salient pole synchronous machine, wound rotor salient pole synchronous machine, LD is greater than LQ. For this IPM, it looks cylindrical, but it is actually salient, and the saliency is opposite. LD is less than LQ. This is also sometimes called reverse saliency. Reverse saliency. LD is less than LQ. Okay. Any doubt in this discussion? Okay, if not, then we will move forward. Two types of synchronous machines. One is called autosynchronous. I don't think so.
उसको बोलो कल Mohammed is there. So maybe you can come and pull me there in G002. See, I may finish my topic and then I want to show some slides. Pendrive मेरे पास रहेगा, मैं pendrive देता हूँ. तो इसे देखिए, तो लैपटॉप देखिए. 9 o'clock के पहले आने की जरूरत नहीं है.
Okay, sorry for that. So yeah, so this is done. One last thing we will discuss about starting of synchronous machine. Starting of synchronous machine. This is actually very interesting, and this will lead to many more interesting discussions. And to be very honest, all these discussions that I had this and this will actually open the gateway towards higher studies of machine. You will at one time understand that all machines, maybe except induction machines, are synchronous machines. Anyway, that may be too general a comment, but
Sir,
okay, yeah.
so what are the current research that is going on these machines?
Why?
What are the current research topic that is going on in these machines?
Research topic, see, there are several things to say here actually. This PMSM BLDC, actually they were there, but the problem was with the magnets. Okay, initially we had only ferrite we had, then alnico came, but ferrite, alnico, these are very how to say, weak magnets. Say if I draw the BH curve, say ferrite is somewhat like this, alnico is somewhat like this. Okay, let me draw it another color. If it looks surprising to you, you can keep the questions, but I don't think I can answer it today. That why am I drawing the BH curve in the second quadrant? Is it known? Ferrite is this, alnico is this. Okay, they are very low, very weak. So although this machine came, they could not do well compared to the other round-filled machines. But revolution started as soon as magnets like samarium, cobalt, and neodymium iron boron magnets came to the market. They are super powerful. And nowadays, and as a result, say around, it started from 1990s, PMSM, BLDC, they started gaining popularity. Lot of research started. I am not exactly working on, I'm not working on these synchronous machines though, but more or less the research trends are, one thing, this is the advantage is the high power density. So increasing the power density, increasing the torque density is one, then different types of shape of IPM, and then different types of control, maybe vector control came here, although it was already introduced for induction machine. Then Let me recall what my colleagues talk about. Winding wise, like improving winding factors, but those are classic quirks. Then control, then this kind of thing, say for example the two torques that I talked about, reactance torque looks like this, and then with delta, and reaction and reluctance torque looks like this. So the summation is somewhere here, optimizing that ratio, this kind of work to so as to get the maximum power out of it. Then what came is EV boom came. With EV, what people started doing is that, see, this IPM, if you see, the problem is um, how to tell that IPM, it is easy. IPM, the effective air gap is less. SPM, effective air gap is more. So IPM, it is easy to demagnetize. Or SPM is easy to demagnetize. Just a minute. Huh? Yes, it's easy to demagnetize. It can have a large field weakening, but has other problems. So that is the one. But the problem is with the magnets. So what I'm seeing nowadays, people are again shifting back to hybrid excitation, or to say hybrid excitation synchronous machines. That is synchronous machine that will have both permanent magnet and winding, permanent magnet and winding as the excitation, that will have a very large field weakening. For electric vehicles, field weakening is very important. That is how fast your car can go on highways and all, where you don't need much of torque. And that is one thing. Another part is for the reluctance machine. This is actually my domain. A reluctance machine, there are two types fundamentally. One is the switch reluctance machine, which is probably the very first electric machine ever invented, and another is the synchronous reluctance machine. Now switch reluctance machine is a salient pole machine. This is what I am directly working on, and synchronous reluctance machine is a cylindrical rotor machine. The difference is that it's a concentrated winding machine, and the magnetic field moves in step, like say the second hand of a clock, whereas this one, the stator is identical of a synchronous machine or a induction machine, PMSMB is whatever. So the magnetic field rotates smoothly, and the rotors look different. Let me show you. Synchronous, CHRONOUS, reluctance motor, synchronous motor rotor. I will show you just the rotor. Let me get a good photo. Yeah, this one is good. Although this has this has only the rotor. Yeah. So this is the rotor of a synchronous reluctance machine. As you can see, the Q axis is here. So this thing is made of steel, and they have cut in between this, right? So this is called flux barriers. This white part is actually vacant flux barriers, and this part is called ribs. These parts are ribs. Okay. And so the flux, as you can see, the flux can flow in this direction, rotor flux, and it cannot flow in this direction. So this can be conceptualized as something like this. So if I draw on exactly on this can be conceptualized as something like this. You have a lot of reluctance, permeance here and here and here and here, whereas very less permeance on the other side, right? Like this. Now, what people are doing nowadays days on this machine is, one is definitely optimization of the barriers and rib barriers. You can understand that there are several design parameters here, right? Several dimensions. Say this thickness, several dimensions, optimizing that. Now, second, one thing that you have to keep in mind in optimization, that you cannot make them very thin. They will break at the highest speed. So that kind of simulations also you have to keep handy. That maybe you have done something that is very good in terms of electrical performance, but it's very poor in mechanical performance. So that cannot be a solution. That is optimization rim, one thing. Another part that is very popular, that is PM assisted um, synchronous reluctance machines. What they do is they put permanent magnets here, mostly ferrite, mostly ferrite, mostly ferrite. So here, why do they put permanent magnet here? What is the objective? The objective is simple. See, I do not want what I want. I want LD by LQ to be maximum, so as to have the maximum amount of torque out of the machine. Now, even if along the Q axis you have several flux barriers, flux can still flow, right? It will just see a larger reluctance, the flux can still flow. I will try to minimize the Q axis inductance as much as possible. So the objective is to put permanent magnets in these flux barriers and increase the flux density. Increase the flux density. Just a minute. Where to? Increase the flux density a lot in these areas. So if you increase the flux density a lot in these areas, what will happen is they will saturate. They will saturate, and saturation means, as we discussed, inductance will drop. So d-axis inductance will even more drop. That will increase the saliency ratio. You will get more torque. So that is the concept of PM assisted synchronous reluctance machines. So this is one very popular. Another one is, as I said, shaping the bars, and these machines are now gaining application in very high speed application motorings, also motorings generating. So they are, along with electrical research, mechanical research is also going on. You cannot simply doing electrical simulation and then find out that the machine breaks when you run the machine. So that kind of work is going on. And that's all I know about synchronous reluctance machine. And
Sir, yes, simulation, in which software you use for the simulation?
we use in our institute, we have licenses of two softwares. One is ANSYS and the other one is Magnet. These two softwares we use. Generally, one scholar uses either ANSYS or Magnet. Okay, they are equivalent.
NCC is more.
Sorry. Okay, so this is what
NCC is better, sir.
I don't think we can make a comment like that. I don't know.
It's like complex problem, you know.
See, any software runs that same algorithm in the background. That is a finite element analysis. Okay, and then you have to model. The result of your finite element analysis software very much depends on how accurate your modeling is. The software doesn't make a mistake. How accurate your modeling is.
Yes.
ANSYS definitely has a lot of packages. That is one um, advantage, but we cannot compare like that. At least I don't know, because I do not know both the softwares. I use only one. So yeah. Anyway, there are other softwares also. If you want to try, you can try.
Console.
COMSOL, yes, COMSOL also we have license, but I have, at least in our group, I have not seen machine design people working using COMSOL, but I think it can be used. And there is one software named FEMM. This is also a FEM software, and it is free open source software, so you can use it if you want to see, or ANSYS student version also you can use and see. Okay. All right. So synchronous reluctance motor, switch reluctance motor. Um, it looks like this. I will quickly show you a photo. Switched reluctance motor. Once you see the diagram of switched reluctance motor, you will understand that it is the simplest machine that one can imagine. That is, if you know how to make electromagnet, and if you know magnet pulls iron, then this is the first motor that will ever come to your mind, and that is what happened to human being. The first ever machine to come to their mind was this switched reluctance motor, right? So it's like this. Suppose this rotor, so it's a double salient machine, probably the only double salient machine, or apparently double salient, as we saw that IPM is also a double cell, not double salient. Oh, okay, no, this is the only double salient machine that you will see. I do not think there is any. IPM is salient, but only on the rotor. So doubly salient, both the stator and the rotor are salient. Suppose this rotor is rotating in this direction when this winding is excited, so it will pull the rotor towards itself, so that the reluctance is minimized. And as long as you see it reaches here, this it reaches, say, in the, say, 1 2 3, in the third diagram, if you see here, now if you turn on this phase, it will keep rotating in this direction. So this is the philosophy of switched reluctance machine. So now you can understand one thing here, that you cannot simply keep on firing the phases. You have to know the position of the rotor, the angular position of the rotor. Based on that only you can fire the phases, you can turn on the phases. That means there needs to be something that would control the phases, turn on and turn off of the phases based on the rotor position, right? So this is where the problem of SRM came. It is also called SRM. SRM came when it was first invented in the 1800s, in the, means the 19th century. They did not have power electronics, so it was difficult to excite the windings based on the rotor position. So after some time, induction motor came, where you don't need anything, simply plug it, it will run. Switched reluctance motor went out of the picture. Again, when maybe in the 70s or 80s, 1970s, 80s, when thyristors first came, and then gradually other power switches, SRM again came into picture, right? So this is where we can pick up with the starting. It's a good point to pick up with the starting of synchronous machine and the two types of synchronism, self-synchronous and true synchronous. Starting, okay? So a synchronous machine can be simply visualized as one electromagnet pulling another electromagnet, okay? When, since I'm talking about starting, obviously I'm talking about motor, right? So the one electromagnet pulling another electromagnet, simple. Synchronous machine. Now you have a synchronous motor, you have a grid, and you connect it to the grid and turn and close the switches. Instantly, what happens? Instantly, the stator the stator field starts rotating at the synchronous speed, which is given by 120 f by p. Maybe in India 3000 rpm for 2-pole machine, 1500 rpm for 4-pole machine, and so on. So the rotor was static, a heavy metallic rotor, static. Suddenly you ask it to rotate at 1500 rpm. It cannot rotate. You can do this mathematically also. Torque is proportional to sine delta. Now, if it is rotating so fast, average of sine delta becomes 0. So synchronous motor cannot start. A synchronous motor is not self-starting. It is not self-starting, cannot start if you directly connect it to a grid. Okay, it will not start because suddenly the field starts rotating at very high speed. It cannot keep up. It cannot keep up. So what is the way? One way is to start it as an induction motor. Look at this figure of the synchronous reluctance machine that I copied from the internet. See, along with the flux barriers and ribs, it had something else. It had squirrel cage slots. Similarly, you can do the same thing for a synchronous machines also. Any synchronous machine, squirrel cage. So what happens is, this is also, just a second. This is also called damper winding. I will tell you why. Damper winding. So what happens is once you once you connect the the synchronous machine to the grid, this squirrel cage slots, they start carrying current. Why? Because they are seeing changing flux. They are seeing changing flux. So they start carrying current and the machine starts as an induction motor. And we know that induction motor at steady state, it is very close to the synchronous speed. So once it starts as the induction motor, reaches somewhere close to the synchronous speed, then it locks on to the stator field, which is rotating at synchronous speed, and then it keeps rotating as a synchronous machine. Now, when the synchronous machine is rotating at the synchronous speed at steady state, suppose there is no speed fluctuation, then the current through the squirrel cage slot is 0. Okay, current through the squirrel cage slot is 0. Now suppose there is a speed fluctuation. The speed increases or decreases. What will happen is there will be current. There will be current through this through this damper winding. If I extend this torque speed curve, it is something like this. So if the speed reduces, there will be a current in the damper winding that will give a positive torque and move it again, push it towards the synchronous speed. If the speed increases, there will be braking torque due to the currents in the damper winding, and it will again push it back towards the synchronous speed. That means the presence of this cage, induction motor like cage, damps out any oscillation in the synchronous machine. It is giving more stability in terms of speed to the machine. That is why this is called a damper winding. Okay, that is how you start a synchronous machine. Means if you have these windings, you can start DOL. Now this is what they had many years back when they did not have power electronics. Now we have inverter. Now we have inverter. So it's not very difficult to start. So what we have is the three-phase grid, and the three-phase grid, since we have to run an inverter, first comes a diode bridge to make it DC. Sorry. Then an inverter. Okay. So this is a rectifier. This is inverter. This inverter runs the synchronous machine. Okay. Now, how is it helpful? Is it helpful in the sense that there is a speed sensor? A speed sensor that regulates the switching frequency of the fundamental switching frequency of the inverter. Okay. So it starts from very low switching, very low frequency, so that machine can start, and gradually increases the frequency. Okay. So the induction, so the synchronous machine that is directly connected to grid, is called a true synchronous. It is a true synchronous, whereas synchronous machine, as I told you, that all these machines are actually synchronous machines. Synchronous machine, PMSM, BLDC, switch reluctance machine, synchronous reluctance machine, all of them are actually synchronous machines. So any synchronous machine connected to or driven by the inverter circuit that is definitely having a position sensor is an auto or self-synchronous machine. Now, for the true synchronous, you can understand that suppose something happens, say sudden heavy load or something, and suppose the speed drops to half or something, sudden change of speed, the machine may instantly fall out of step. It may instantly stop. It may not be able to follow the stator field again. Maybe you have to start it once again. On the other hand, for the auto synchronous, it's not like that. If the speed suddenly drops, or if there is a huge fluctuation of speed, that data is instantly relayed to the inverter, and the inverter adjusts the switching accordingly. So they are very less likely to fall out of step. Okay. So these auto synchronous machines, they are always in synchronism. At the starting also they are in synchronism. The frequency of the stator winding supply is determined by the uh, rotor speed. Determined by the rotor speed. Okay. The DC machine, see, actually these discussions will keep on going. The DC machine also has a position sensor. Where is it? Did you see position sensor in DC machine? Actually, the commutator brush gear arrangement in a DC machine, that is a pseudo position sensor of the machine. Why so? Because whenever one terminal of a coil crosses one brush, the current polarity through it reverses. That means the commutator decides when to reverse the polarity of the current, just like an inverter, right? Now, people wanted to get rid of this commutator. People wanted to get rid of this commutator. So DC machine, what did they have? DC machine, what did they have? On the rotor, they had armature. On the stator, they had field. They said if the rotor is on the armature, we will need commutator brush gear. We do not want the rotor on the armature on the rotor. We want the armature on the stator. We want the armature on the stator. Very nice. We get the armature on the stator. Okay. And what will be there on the rotor? Rotor must be having permanent magnets. Otherwise, again, you have to have a slip ring brush gear for the field, like a synchronous machine. Very well then. Now we have no brush, but the machine that we get here by doing this, by switching the rotor and the stator circuits, is BLDC, brushless DC, no brush. But the problem is commutator is gone. We don't know when the stator should carry, when one certain phase of a stator should carry positive current, when it should change polarity and carry negative current. We don't know. So who will decide that? The position of the rotor, or better to say the position of the q axis of the rotor with respect to a certain phase, or that phase will decide when the current will flow. For that we need a position sensor. So BLDC cannot run without a position sensor. You may accidentally run it in steady state at no load, maybe for some time with position sensor, but if there is something here and there, it will go out of step. Like a synchronous machine. Once you have position sensor, you know where to fire the phases, and you have a very steady operation. You can run it at any speed, means you have full control on it. And as I explained just before, the same goes for synchronous machine, this switch reluctance machine also. You need a position sensor to know when to turn on which phase. So basically these all synchronous machines are the same in operation. Their current waveform is different, their magnetic fields are different. That is where the major difference comes, but fundamentally they are all the same. Okay, so I hope this idea you will carry forward. All right, so any question from here?
No, sir. Thanks, sir. Now we can solve the problem.
Yeah.
Okay.
All right. So a round rotor delta connected synchronous generator is feeding power to a 380 volt line to line bus at unity power factor. The excitation voltage is this much. Synchronous reactance is given. Armature resistance is negligible. Estimate the armature current per phase. So it's a delta connected. So supply voltage is same as line, sorry, phase voltage is same as line voltage. You can quickly draw the equivalent circuit. Looks like this generator. So let us take in this way. Doesn't matter. You should be very flexible in doing all this. In whatever direction we can draw the current, voltage, whatever, it doesn't matter. See, in this circuits I did not draw the plus and minus. Just assume that the top is plus. Otherwise, see, unless I draw the plus and minus signs, the circuits are not valid. They don't convey anything. I can't even write the KVL out of it. Okay. All right. So what is the equation then? E is J I x plus v. And it is feeding power at unity power factor. So feeding power, so this is v. Now see, current I is entering the positive end of v, so this should be like this, v, and with v we add jix, so that should be in this direction, jix, and v plus jix gives us e, the phasor diagram. Now the question is estimate the armature current per phase. Okay, what do we have? We have all the values, don't we? Let us see, excitation voltage 479 is given, synchronous reactance is given, armature. Okay, so we can just use geometry here to find out. Magnitude wise, we can say modulus of E squared plus modulus of V squared is equal to modulus of Ix squared. So magnitude of I times this 2.5, which is the reactance, 2.5 is equal to, sorry, is equal to this minus this, E minus V. What is E? 479 squared minus 380 squared. This should give you a magnitude of current as 6 ampere. Okay, since we don't have much time today, I will keep on doing, and if there is a problem you can stop me. Okay, so estimate the power angle delta in degree. So just from this triangle we can write tan delta is Ix by V. What is Ix? 116.6 times 2.5 by V is 380. So this should give a delta value of 37.5 degree. Okay. Estimate the amount of power fed to the bus. We can do it per phase, then multiply by 3. We saw it last day, EV sine delta by X. Delta is the angle between E and V. This is delta. So the total power P is 3 times EV sine delta by X. 3 times 479 times 380 sine 37.5 degree whole divided by 2.5. That should give some 133 kilowatt. Okay, if is there a problem, tell me. Quite straightforward problem.
So can't we calculate this from like E minus V by X? Simple
minus
formula of I. We don't have delta here.
We do not know the phasor relation between them.
No,
The first problem itself.
E minus V by X.
Oh, which question are you talking about? Which part?
First one, first one.
First one, okay.
Can we calculate this unity power factor delta from that?
See, if I take V as 380 angle 0, I can take
Yes.
I don't know, some value of I angle 0, and E is 479 angle delta. Now you have one equation and two unknowns. Delta is not known, magnitude of I is not known. Isn't it?
Yes.
So one equation, two unknowns, we cannot solve. Okay. So we'll go to the next question. Round rotor star connected synchronous machine has a synchronous impedance of this much per phase. For the purpose of power factor improvement in a plant, this motor is used as a synchronous condenser under no mechanical load. It is required to draw minus 22 kVAR, means it is required to provide 22 kVAR reactive power to a 240 volt bus. I forget this thing in this bracket. I don't know why they mentioned this. Simple, a synchronous condenser supplies reactive power to the bus. It's a overexcited synchronous motor that draws leading power factor current from the bus. Simple. The motor has a constant loss of 2000 watt. Okay. So let us how to do this. It's a star connected synchronous motor. So per phase voltage is how much? 240 by root 3 volt. We have to find out the line current. This is the per phase voltage, and has a constant loss of 2000 watt, and also it is okay. So the power P that is drawn by the motor is 2000 minus J 22 10 raised to the power 3, this much watt. Understood? This is the power drawn by the motor. Now this is the voltage V, is the current I. So we can say V phase, I phase, cos phi 3 times, 3 times V phase I phase cos phi is the active power, and 3 times V
So this
phase.
P will be in watt. What is the volt? What is the apparent power?
Oh, okay. Yeah, true. Sorry. And this should be 22 kilo. Now, so everything is known. Only thing what you don't know here is, so what we can do is from 1 and 2 we can do 1 square plus 2 squared. that will give you from here you can find out the phase current, which is also equal to line current because it's star connected. Can you just do it? It should be 53 ampere. Ampere. Okay, and from here we can also it is not asked, we can also find out cos phi. Cos phi should be, basically I'm trying to find out phi, 2000 by 3 times 240 by root 3 times 53.1. So from here if you find out phi, that should be cos inverse 2000 by 240 root 3 times 53.1, 84.8 degrees. See how much it is leading, 84 degree. Obviously it's 2 kilowatt active power and 22 kilowatt reactive power, so this is the angle. So the current phasor you can write as 53.1 minus 84 or plus 84? Plus 84, current is leading. Okay, this is it. This is the current. Now the question is estimate the required excitation voltage per phase. So it's a condenser. Taking V as this and I as this, we did the calculation. So when I am taking V here, I have to take, it's a motor. So in this direction, then only it can supply power. V I. Now with this, I can write the phasor equation KVL. That is V is equal to IR plus JX plus E. Now you have to do a vector calculation here. You can do by splitting into sine cos. You can do by what is it called? 240 by root 3. You can do by using a calculator. By root 3 angle 0 minus 53.1 angle 84.8 degree times R plus JX is given 0.15 plus J 6.4. This you can do in a calculator, and what you will get is 478 angle minus 4.64 degree. Let us quickly check. Is it matching? See the overexcitation that we did, overexcitation phasor that we derived last day. E was lagging V. Here also in the calculation, what we are getting is E is lagging V. Okay. All right. Estimate the power angle delta. So the angle between E and V, 4.64. Motor is overexcited. All right. Last question. It's about the only question about salient pole synchronous machine. So we had a lot of discussion about salient pole synchronous machine. It can give you both type of torques simultaneously. This derivation you will get in the lecture. I'm just writing it down. So if you see, power is 3 times. The first component is same as the cylindrical rotor machine, xd. Why xd? Because there is the highest inductance through which the field flows. This is same. Now another component that comes due to the reluctance power is this 1 by xq 1 by xt sine 2 delta. This comes from the two reaction theory of salient pole synchronous machine. Now, one important thing or interesting thing to note here is the frequency of the power with respect to delta. See, the first component, this one, which is the reactance torque or reactance power. Sorry, not reactance, reaction torque. Reaction power, and the other one is reluctance. See, the reaction power, it varies with sine delta, whereas the other one, it varies with sine 2 delta, twice the frequency. So if you draw power versus power versus delta plot, the red one is the reaction. Here you have delta equals 180. Here you have delta equals 90. Delta equals 90, you have the maximum reaction power. Whereas reluctance varies like this. So the red one is reaction power and the green one is reluctance power. If you add them up, maybe something like this you will get. This is very much on the machine, how the machine is designed. Somewhere like this, maybe. No, sorry. How should it look? Here it is 0, so here should be equal. Yeah, some out like this. It will look like this total. So you see, the peak torque does not appear at the 90-degree anymore, somewhere else. So if you can manage to control delta, at that point you will get the maximum possible torque out of the machine. This is also true for the IPM that we had a little discussion on. Also true for the IPM. Whereas for the SPM, you have only the sinusoid. We don't generally, no, we can operate something called at unity internal power factor, so that you can have the maximum torque per ampere, maximum torque per phase current from the machine. And since it's very stable IPM, since it is being run by an inverter, you can easily maintain and control it close to 90 degree, or at 90 degree actually. Okay, but that does not mean that you will see unity power factor at the terminal. That does not ensure maximum power. Maximum power means current should be in phase with E, back EMF. Okay. All right. The star connected salient pole synchronous motor to 10 volt infinite bus star connected. So you have to change the voltage to phase at XD, XQ, negligible armature resistance. Open circuit excitation 190 line to line. So basically just convert E and E and V to phase voltage. Everything else is given. Load angle is also given. So they said 25 degree, maybe, we don't know, maybe that is where it is getting the maximum torque. Estimate the gross mechanical power. Just replace the values, substitute the values. You should get close to 17 kilowatt. Okay. If the fuse in the field circuit is blown, so fuse in field circuit is blown means you have lost the reaction power. Basically E is off, E is 0. So this means E is 0, no back EMF. You are only relying on the reluctance now. Then the motor will keep on running or not. Here one very important thing is the motor is operating under a constant load torque. This is important to answer this question. If it is a load like say a fan load, means a turbine or something, then the motor will keep rotating at low speed, because there low speed means low torque, so it will keep rotating. But here it's a constant load torque, maybe an elevator. Okay, so we have to find out the torque or find out the power maybe, and see whether that is actually, there is no need to calculate anything here. Sine to delta. Okay, so the question is, when there is no back EMF, only we are relying on the reluctance torque, can we keep on delivering this torque? So at some value of delta, let us consider that was the optimum value, 25 degree, it was operating before the field blew off. Now the field has blown off. There is no point of keep on operating the machine at 25 degree. We will keep operating the machine at such a value of delta such that sine del 2 delta is equal to 1. That is where we get the maximum possible reluctance torque. So where we get maximum reluctance torque, sine will equal 1 means 2 delta is 90 degree. So delta is 45 degrees. So we will operate the machine at delta equals 45 degrees so that you can get the maximum reluctance torque. So under this condition, what is the power that we are getting? It is v square by 2, 1 by xd, sorry, 1 by xq, 1 by xd times sine to delta, which is 1. So now if you calculate this will come out at 16.53 kilowatt, which is less than 17 kilowatt. So it cannot rotate. It will come to a halt. Okay, any question?
Sir, how we come to know कि it is operated 45 degree from the given question?
No, it will not come to know. We did not come to know. See, if you do nothing to the machine, what to say, it will keep operating at the same delta. But here we are trying to find out a possibility whether it can operate only as a reluctance machine. It cannot, because even at the maximum reluctance torque, the power is less than the required power.
Okay, okay.
Okay, now since we talked a little bit about modern machines today and discussions about this synchronous power and all, I mean, it's not synchronism and all, led us towards discussion of true synchronous, self-synchronous requirement of position sensor in electric machines. We will end today's class today's as well as this course with the discussion of something that is a very important component of modern machines, that is permanent magnets. We will have a short discussion on permanent magnets, and we will stop today's class as well as complete the course. All right, so the internal physics is known. There are magnetic dipoles. You align them and get a magnet. So every ferrous material is actually a permanent magnet. Question is, how much is the remanence? How much is the remanence? I will draw two BH curves. Okay, say one looks like this. Okay, it should be symmetric, just cannot draw like that. Another one, it's like this. Which one can be a permanent magnet? This one, hard magnetic material. Whereas this one is an electric steel. This one is an electric steel. Right? Now suppose you have a piece of suppose NdFeB in your hand, and you are trying to magnetize, say, of the bar, and you are trying to magnetize it in this direction. Okay, so what you do is you take it to a solenoid. Take it to a solenoid. And supply a DC voltage momentarily. Large current flows, B comes up. Now suppose you have a control on it. Let us say you have a control on it and you are trying to plot a graph. Okay, what graph are you trying to plot? You are trying to plot a BH. Okay, I did not write BH. You're trying to plot a BH curve. This is H, this is B. Now listen this in very carefully. Suppose you have a sensor here that is measuring the value of B, and you have an ammeter which is measuring the circuit current, which is an indication of the value of H. Initially, the NdFeB block was completely demagnetized, so we start from here. Okay. Now, Just a second. Yeah. Now I keep increasing H. B keeps increasing. B keeps increasing. Saturates, goes like this. Now the thing is, if you keep increasing B, it will keep increasing. So keep increasing H, the circuit current will keep increasing. Now there is something that is called an internal characteristic and an external characteristic. These things are very important, and try to get the concept clear. Internal and external characteristic. See, after a certain point, you cannot magnetize it anymore. You cannot magnetize it anymore because all the dipoles are now aligned. And it looks something like this. It looks something like this. Okay. So basically, when you are keep increasing the H, what you are getting is on this constant value, something is increasing linearly. So you get a linear curve here. Now when you decrease, it comes by this and resides here. And then when there is a negative H, it goes something like this. When H is equal to this internal, it becomes 0, comes down, goes like this. So this blue one is the external, green one is the internal. I will quickly show you one data sheet of a magnet. Let us see. This is to tell you how to read the data sheet of a permanent magnet. Well, this diagram looks nice. Nothing can be read, not legible, just look at it. So this red one, the red curve that you see here, is the internal characteristic or intrinsic characteristic. And the blue one is the extrinsic or the normal characteristic that we get outside the magnet. Right? Now all the calculations, all the design of magnets that we will do in terms of external characteristic, not the internal. Okay. Now let us look at the, actually this requires some calculations. I don't know. Let us quickly do. Suppose you have a magnet. You have a magnet placed in a iron keeper. This is called keeper, made of iron. Have you ever bought a magnet? If you buy a magnet, you will see the magnet always comes in a keeper. This is what we call the magnet is short circuited. Short circuited. A magnet is nothing but a current source. See, we many a times draw electrical equivalent circuit of magnetic circuits. The battery equivalent is a solenoid. voltage equivalent is mmf, and the current source equivalent is a permanent magnet. So just like you have to keep a battery open when not used, you have to keep a current source short circuited when not used. Similarly, this has to be kept short circuited, magnet has to be kept short circuited when not in use. We'll look into it in detail mathematically. Now, you cannot keep a magnet keepered throughout your life, because in that case, how would you use that? If you have to use the magnet, you have to take it out of the keeper, or maybe make a cut in the keeper where you can get the magnetic field. Now suppose this is where I made the cut. This is where I made the cut in the keeper. So there is an air gap. Let us say the length of the air gap is Lg. Area of the air gap is Ag. Say throughout the circuit the area is same. Length of the magnet is Lm. Area of the magnet is Am. Right? Now I will apply KVL. KVL. See? So how does it look? It's HM LM. So what I'm taking is the keeper has a permeability of infinity. Okay, so there is no mmf drop in the keeper. So HMLM plus HGLG is 0. Right, I am taking all the direction as same. Flux is flowing in these directions. HMLM plus HGLG is equal to 0. So this gives you HM is minus of HGLG by LM. That means when you are not making a cut in the magnetic circuit, when you are keeping the magnet in the keeper, the magnet is operating here. The B that you are getting is the remnant flux density, Br. As soon as you make a cut, H becomes negative. H becomes negative. And you have come into the second quadrant. This is why there I drew the magnet in second quadrant. It comes in the second quadrant. Okay. Now, if you do a little bit of more thing. Okay, now suppose we are trying to understand. Okay, it's in second quadrant, understood. Now, but where is it operating? Just like in a circuit, when we calculate say voltage and current, and we have something like this, and this slope is 1 by r. Similarly, something like this we can do in the magnetic circuit also. How to do that? Let us see. So for the air gap, we can write Bg is equal to mu naught Hg. Okay. And we can also write that Bg is equal to Bm, assuming that there is no fringing, the flux density remains same. No, sorry, we cannot do that. The flux is same flux keeps going, area is different. So if phi m is equal to phi g, then magnet, so this is what the B is, B by area, sorry, B dot ds. So B times am equals Bg times Ag. Let us see what we have got. HM equals minus, so Hg is Bg by mu naught, Bg Lg by mu naught Lm, and Bg is Bam by Ag, so minus Bam Lg by mu naught Lm Ag, right? So now if we write this equation in a clean way in y equals mx format, see this h is the h of the magnet and b is the b of the magnet. So let us write in b and h. So y is b. So b becomes minus mu naught times Lm Ag by Lg by slope comb times h. So this is how we get the value of b and h. So now this equation that we get here is called the equation of load line, and this factor here, this is called PC, permeance coefficient. So this is the characteristic of the source that we have here, and this is the load line whose slope is given by PC. The intersection is the operating point of the magnet. Let us see what happens if we increase the air gap length. PC reduces, slope reduces, this falls, so magnet goes down, means we are getting less value of B, and the least value of P of PC is when Lg is 0, PC is infinite. So this is the short circuit condition when magnet operates here, right? Now we don't have much time, just do one more thing, one last thing. So when you put a permanent magnet in a machine, just say the machine is resting on the table, it's not excited. Okay, forget excitation machine and all, or you can consider whatever. Where does it operate? Is it short circuited? It is not short circuited because there is air gap. So maybe it is operating somewhere here. It is operating somewhere here when the machine, when the machine is just kept on the table. So as soon as you remove the keeper from the permanent magnet, your magnetic field has already dropped to here. Beyond that, now if you have, say in this circuit that we drew here, the circuit, keeper circuit that we draw here, now you can have another current source, another voltage, whatever, another Ni source, MMF source, that is opposing the magnetic field. What will happen is this line will shift, load line. Slope will remain constant because slope is completely a function of geometry. So this is proportional to the applied MMF. It will shift. How much can you shift? This is irreversible. So suppose this is the BH curve of a magnet. Short circuited. Now suppose you are applying some external force to go down, say up to this. you'll again come back through this line itself. But if you accidentally cross the knee and go here, you will not come by through this line. You will come by somewhere like this. Actually, there is a small loop, but you can neglect that. So this is called the recoil line. It changes as soon as you demagnetized, the recoil line changed. So this, now even if you keep the magnet short circuited, this BR you will not get. You will get this BR. So the magnet is permanently demagnetized. You have to again magnetize it to use it. So this is one hazard of the permanent magnet machines. If there is something wrong, especially when you are trying to go to the field weakening mode, there is a good chance that if things go wrong, magnet will get demagnetized. So suppose the BH curve looks something like this, say at 20 degrees centigrade, at 100 degrees centigrade, it looks something like this. So there is a good possibility of demagnetization at 100 degrees centigrade, maybe. Okay, so you have to make sure while designing the machine that even at the full load or full field weakening, you are not crossing this knee. You must not cross this knee. Your magnet will be completely demagnetized. You have to remagnetize it again. Okay, so that's all from my side for this course and today. If there is anything else. So thanks for attending, especially to Mr. Dinesh. I should say that I'm lucky to have such a student every time who attends the class. Otherwise, most of the case, the student curve declines like anything. First day, some 15-20 people will come, then it will reduce.
So in the written that exam, the problems will be like what we are solving.
Yes, I think so. I have not seen though, but I believe it will be like that only.
Okay.
Okay, thank you for attending. All the best for your future endeavors. Thanks a lot. Bye.
Thanks a lot. Thanks a lot. Bye.